Hello, I hope you can hear me. Good morning, good evening. Welcome everyone to our SFP Greater London Student Chapter webinar series. My name is Francesca and I'm the current president of the SFP London Student Chapter. And I will today introduce our presenter. We're very happy to have Dr. Xinyan Huang today. Xinyan was a PhD student at Imperial College in the research group Imperial Haze Lab, of which I'm happy to be part of. So we're very excited to have him back here virtually in London to present to us. After his PhD, Xinyan moved to Hong Kong Polytechnic University, where he pursued a very successful career. He's done a lot of research in a lot of different fields. And he's now an assistant professor at the Hong Kong Polytechnic University. In the recent year, he's won many awards, including the very prestigious Prolux Early Career Award from the IFSS, International Association of Fire Safety Science. And he's been carrying out research in many fields. And today we're very lucky to have him presenting on one of his latest research about dripping fires and the phenomenon of ignition due to dripping fires. So before we start, I just want to say two very quick things. If you like what you're going to be, if you like this webinar, today's webinar, we have plenty more webinars organized for this month, next month, and for the summer month. You can check our upcoming webinars on our website by scanning the QR code or searching on Google SFP Greater London Student Chapter. You can also follow us on Twitter using the handle on the slide, where on Twitter we give updates of all our upcoming webinars and events, or you can follow us on Twitter. If you have any questions during this presentation, please use the Q&A function on the Teams platform to submit any questions that you have. Me and Matt will be reviewing these questions and we will post them. Once we post them, they will be made publicly. Everybody will be able to see these questions. And after Xinyan is finished with his presentation, Matt will try and ask as many questions as possible from the ones that you have submitted in the Q&A. If we're not able to ask your question and you want to know more, you can contact Xinyan directly. And yeah, I think that's it from my side. So Xinyan, if you're ready with your slides, I'll pass it on to you. And thanks everybody for joining. We really hope you will enjoy today's presentation. Xinyan, if you're ready.
Yeah,
great.
I think I have shared my screen.
Thank you. I'll pass it to you then.
So you can see my screen now?
Yes, we can see everything.
Okay, thank you, Francesca. So it's my great pleasure to present back to London virtually. And today I want to share some of my latest research, and it's on the fire hazard and ignition limit of dripping. So that's some topic I have been recently interested for the last 3 to 5 years. And my PhD student, Ms. Pei Sun, is currently doing a thesis on this topic, and my postdoc, Dr. Cai Xiong, is helping me with some of the numerical simulation, which you can see in today's talk. So I just made a slide today, so I'm not sure how long it will be, but I think it will be like 30 minutes, no more than that. Okay, so let me start with a very short introduction about the dripping fire phenomenon. So I'm showing you CCTV footage of a dripping fire inside a room, a storage room. Actually, I'm not sure what's really burning on the top of the ceiling, but you can see something is falling down and likely coming from a cable or some burning plastics. And these drips will eventually form a pool fire on the ground. So it's quite dangerous in a certain way. After just 10 minutes, almost getting close to the flashover, just by dripping some plastic fuse from the ceiling. So it's actual fire hazard in our daily life. So that's common in the compartment. The other thing very common to generate the dripping is cable fire. So I like to show this video a lot because it just shows both the cable fire and the dripping fire, how dangerous they are. So you may think the fire is gone, but no, it's not that easy. So the cable will keep burning, and you can see a lot of plastics are falling down, and they carry the flame. If there is a car below it, it can easily ignite something below it, so generate a new fire. So these are the danger of the dripping. It's kind of remote ignition. Okay. The other example for the dripping fire is facade fire. So I'm showing you here is a fire in 2009. It's this TVCC building in Beijing, China. So this fire is very special. So it is ignited by the firework because it's on the day or the night of the Chinese New Year. So people are playing firework around it. So the firework ignites the top of the ceiling of the building. And within 5 to 7 minutes, the fire spread from the top to the bottom very quickly. Usually you only see the fire spread from bottom to up in a very short time, but this one is coming from the top. So it is believed that the drips, so the fire generates a lot of these plastic drips. They drop down. You can see these particles. Some are plastics, some maybe metals. So they are contributing to the fire spread. Okay. So this is the case. There are many other cases. For example, the Bolton fire in London. I remember it was I think it's a dormitory, university dormitory. You can see a lot of these plastics just drop down. Some are not fully melted, some are still solid. You can see it contributes to the downward march. It's very common. Another one from Korea last year. You can see that a facade fire is very often accompanied with these dripping of the plastics. And some are very big pieces, some are very small pieces. You can see it's a very common fire phenomenon. Okay. So this is just a free, very short introduction about the dripping fire phenomenon. Hope you guys have some idea about it. And I just want to share some sciences today behind these dripping fire phenomena. I try to limit the number of equations. Should be only 2 of them, I guess. The time I noticed the dripping phenomenon is actually back to 10 years ago when I was doing my master's thesis on electrical wire fire. So at that time, I'm burning very thin wires. Sometimes I see these drips coming from these small flame. And sometimes after drip, the flame will extinguish because I feel like it's quite safe if the drip can remove the fuel. But sometimes it's very dangerous because it can ignite things below it. And later on, I'm trying to burn larger wires. This is a relatively thick wire, and there's a lot of drips. And if I put that in a wind tunnel, these drips then can fly with the wind. So it's kind of massive. Sometimes it forms a pool fire below it. So this is how I get interested in this dripping fire phenomenon. And the first thing I want to answer is how these drips are produced, why they are produced. So if we take a close look at of the production of these dripping, so you can see it initially is a part of the plastic, and after a while it just gets detached. So basically there is a force involved. So one is the gravity force, the other is the surface tension force. And when the gravity force overcomes the surface tension force, then you will generate a drip. So there is a very a simple relationship here. So why sometimes the gravity can pull the melts down, but sometimes cannot? The major reason is if you have a flame, the flame will heat the plastic, and the surface tension of the plastic will decrease with the temperature. So if the temperature is very high, the surface tension is small. Eventually, it cannot hold the fuel. Okay, so this is the first condition. So how these drips are generated? And the second question I want to answer is why are these plastic drips are so dangerous? We see a lot of drips from candle flame. These are wax drip. So these drips are not really dangerous. I have never heard any fire are caused by these candle wax drip. And sometimes I touch it. It's hot, but it's not enough to ignite something. The difference between the plastic drip and the wax drip lies in the flame. For the wax drip, it does not have a flame, but for the plastic drip, it has a flame. That makes the plastic more dangerous. So why for the wax, it cannot carry the flame, but for the plastic, it can? The major reason is the flash point. For the wax, the flash point is like 200 degrees Celsius. So it's very difficult to ignite the wax unless you have a wick. But for the plastic, it's different. So you can ignite it in the room temperature. And once it ignited, the solid can be continually heated by the flame, so become liquid. Then it can drip. So when we look at the plastic drip, we should not think it's like a wax. It's more like a gasoline drip, because this is the hydrocarbon fuel. So it's like an oil drip. And it burns exactly like this droplet combustion, really fast way. And the difference is the drip can generate a lot of bubbles. So that's the only difference between that the plastic drip and the gasoline drip. So now we know that the plastic drip is more like a gasoline drip. Then I want to answer, can the drip always cause ignition? So to verify that, I try the simplest fuel, or maybe the easiest fuel to ignite is the tissue paper. So I want to see whether this single drip can ignite that tissue paper. And the result is very surprising. So sometimes you can, sometimes you cannot. So what I'm showing you here is, you can see the top video, the tissue is ignited by one drip. But the bottom video, I have like 30 drips landed on the tissue, but it still cannot get ignited. So that's the difference. What's the difference? The difference is flame. So if the drip can carry a flame, it can ignite the tissue paper just one drip. If it does not have a flame, even you have like 100 of them, you cannot ignite even a tissue paper. So here is a key thing here. So in order to get ignition, you have to have a flame attached to the drip. But the question is why sometimes the flame attached to the drip, sometimes it does not attach to the drip. So to answer that, I try to vary some parameters. The first thing is to vary the size. So sometimes some drip is big, some drip is very small. So when you land it on the paper, you can see it compresses into a thin layer. And of course, larger drips, you have a larger mark. So let me show you from the small drip to the larger drips. So if we use a small drip, and if I close the light, you can see it cannot carry the flame for more than ½ meter. The flame always disappears somehow. It can only travel like 20 centimeters. But if we continue to increase the size of the drip, you can see the drip can carry the flame for a very long distance, more than 1 meter. So it seems like the size of the drip is very important. The flame can only attach to a larger drip. So how long, how high these drips can travel? So I try to push the limit. So I put the flame right below the ceiling and see if it can travel for more than like 3 meters. And turns out it can. If the drip is large, it can carry the flame for more than 1 floor. So the problem is the size of the drip. So if I summarize the result, what I can get is a critical size. So the critical size of the drip is 2.3 millimeter here. So if the drip size is larger than that, it can carry the flame falling down for more than 1 floor. And if the drip size is very small, smaller than 2 millimeter, so it cannot carry the flame. And sometimes if you look at the video here, you can see some tiny drips. These drips, they actually don't go down, they fly up. This is mainly because the buoyancy generated by the flame is actually strong enough to flow it up. So these tiny drips are extremely safe, so we don't have to worry about that. So we only need to worry about these big ones, the big drips, okay? So the question still remains, why the big drip can carry the flame, the small drip cannot? Okay, then we have to take a look at what's a flame look like. So this is dripping by a regular camera, just by my cell phone. So you can see the flame is very different. It's like a chain. It's like a blue chain. So if I'm showing you here, maybe I just show the pictures. So the flame is not. This is actually one drip. I'm not showing you like 12 drips, just one drip. But the flame is like a chain, so like a 12 flame along with it. So very interesting. And later on, I figure out, okay, it's just an illusion, because our human eyes, a regular camera is not fast enough to capture the detailed structure. So if we use the high-speed camera, then we can see the details. Okay. In fact, there is a flame keep generating behind these drips. So, which means it generates like 400 flames in a second. That's the reason we see such a long chain, because our eyes are not able to respond so fast. But the question is, for these big drips, we can see the flame can fly behind the drip. But for the small drips, seems like the flame is not able to catch up with the drip. So how to explain that? We already pushed the limit of the experiment. So the only thing we can do is to do numerical simulation. So I noticed that from the high-speed camera, it's seems like the flame is like peeling off from the drips, piece by piece. So this is very similar to something we have learned before, the common vortex street. So if we have a little sphere, and in a wind, it can generate a vortex street behind it. And this structure is very similar to this one, but of course it is with a flame. To answer that, so we try to do numerical simulation with the flame. So this is the dripping flame after the drip. We do the DNS simulation. And you can see that's the structure we observed from the experiment. And if we reduce the size of the drip, you can see different things. It's actually flame is not stable anymore. So the flame will just disappear quickly. So the flame cannot anchor behind the drips. Okay. So if we try one more time. Okay. So the flame is something like disappearing afterward. So what we can conclude is there are two reasons for large drip can carry the flame. If the drip is large, it has a large wake region to hold the flame, to generate that flame shielding structure. That's one reason. The second reason, if the drip is very small, the convective cooling is very strong, which means the little drip will be quickly cooled by the cold air. That's the reason the little drip cannot carry the flame. So that actually answers why big drips are more dangerous and the big drip can carry the flame to ignite the fuel below it. So this is the first part. We figure out the relationship with the flame and the drip. And then next we have to answer how many drips do we need to ignite actual fuel. We tried the tissue paper. Tissue paper only need one drip, but tissue paper is too easy to ignite. So we try something different. We try printing paper this time. So we're trying to land the drip into the printing paper. Okay. So let me show you one successful ignition. So this case, we put 6 drips onto the printing paper. You can see after a while, the drips can become stable and ignite the entire paper. So this is 6 drips. So if we reduce the number, what if only 5 drips? So okay, after the 5 drips, it cannot ignite it. The paper is only charred. So there is like a critical number here, something between 5 and 6. So for this printing paper, you need 6 strips to get ignition. If you only have 5, no way, you cannot. So if we try to vary the parameter, vary the thickness of the paper, vary the size of the drip, what we can get is ignition probability. So what I'm showing here is the y-axis is the number of drip, and the x-axis is the mass of the drip. So if we increasing the mass of the drip, we notice that a fewer number of drip are needed to get ignition. So this is reasonable, makes sense. And I have to emphasize that the experiment has very big uncertainty. So we use the ignition probability to quantify the limit. So each point here, there are like at least 20 experiments. So we're trying to quantify the ignition limit. And we use 50% ignition probability as a limit. So this is varying the size of the drip. So what if we vary the frequency? We get a very similar result. If we increasing the dripping frequency, we also need a fewer number of drips to get ignition. So it seems like there are 2 main parameters here. One is the mass of the drip. The other is the frequency of the drip. They are contributing equally to the ignition probability, ignition limit. And if the frequency is very small, if you like have 1 drip every 2 seconds, you can never get ignition. So there seems to be a limiting frequency here. If it's not very frequent, you cannot ignite, even you have 100 drips. So that's a key parameter. I will keep using these 2 parameters later. And then we try 5 different papers. Okay, so these papers are different thickness, from very thick one to very thin one. This thinnest one is the tissue paper. And we notice that the number of drips actually decrease if the paper becomes thinner. So that's very interesting. What we can conclude here is it's the paper ignited, not the plastic drip ignited. Otherwise, if the plastic drip ignited, all the paper will require the same amount of drip. And we also can conclude that the dripping ignition is very similar to the pilot ignition, because for the pilot ignition, the thickness will change, the ignition time will change with the thickness. So basically, the dripping ignition is a pilot ignition. Okay, and we're trying to quantify the heat flux of the drip. To do so, we use a thermocouple on the paper, and we're trying to see the temperature of these measurement. So you can see after each drip, the temperature will increase. So there is a peak. And eventually, when the paper reaches 400 degrees Celsius, you get ignition. So this is very interesting. And equivalently, we can get the heat flux is about 13 kilowatts per meter square. So that's from the temperature measurement. So if we look at the high-speed camera, we can see there are actually 2 contributing heating components. One is a hot drip, the other is the flame. So which one is the major heating source? Is this a hot drip, or is a flame? In fact, we did some calculation. We found they are very similar. So the heating from the hot drips is about 2 joule per drip, and the heating from the flame is also about 1 to 3 joule per drip. So they are very similar, and they both contribute to the heating flux. And we tried to quantify the heat flux. We found that is related to the drip of the mass of the drip, as well as the frequency of the drip, which I shown you before. That's the important parameters for the dripping frequency. And later on, we try to quantify the ignition time. So the ignition time, we try to put that data into the classical cone calorimeter result. It turns out these dripping ignition are ignited much faster than the cone calorimeter. So it seems like the conventional theory cannot really explain the ignition time of the dripping. The major reason is there is a time variation here, is the dripping frequency. So if the frequency of the dripping is very high, of course you can ignite in a shorter time. So that makes it different from the experiment of the cone calorimeter. So here we're trying to quantify the ignition time of dripping and propose a new theory. So we found the ignition time is proportional to the thickness of the fuel, but inversely proportional to the thickness, to the mass of the drip, as well as the square of the frequency. So the frequency is really important here. It has it's changed with the parabolic curve. Okay. Okay, that's what we already know about the dripping, but we still have a lot to unknow in this area. I just show you a few videos to how complicated the dripping could be. The first one is to ignite a cotton. So if you put just one drip on a cotton, you can basically ignite it really quick. Okay, you may think it's easy because cotton is very easy to ignite, but let me show you another one. What if the fuel is non-flammable? If we put a drip into a mineral wool, it still can maintain the flame for like 15 seconds, although the mineral wool is non-flammable. Okay, then we try more. We put the metal mesh below it. And if you put a drip on the metal mesh, if you have enough drip, you can also maintain the flame because you already have the fuel. The plastic drips are already the fuel, so you only need to hold it. So what I can conclude here is it's very similar to the candle flame. So it has very strong interaction between the liquid and the solid. If you can get the material soaked with these drips, it's very easy to ignite or maintain a flame. So the interaction between these two fuels are very important. So now we know there are basically two kinds of dripping ignition phenomena. First, it is a pilot ignition. It follows a classical pilot ignition curve. So if you're increasing the frequency of the drips, it will become easily to ignite. And the other one is actually the flame anchor on the soaked fuel. So if whatever material can absorb the drip, it can form a soaked fuel. So you still can maintain a flame very easily. Of course, if you drip onto the ground, then you have to form a pool fire, just like what we tried in the lab. We just burn a chair in our lab and it form a pool fire below it. So that can also work if you can form a pool fire by just dripping the fuel on the ground. Okay. And how do we understand that? So we notice that the dripping is very similar to the hot particle ignition. So if we look at this comparison, if we put a hot particle, it can ignite. If we put a hot drip, it can also ignite a fuel. The reason is dripping is also a spotting ignition because the hot drip is also a hot particle. Okay. But the dripping is more complicated, and sometimes I think it's more similar to the Firebrand. Okay. When you have a Firebrand, you have a lot of these Firebrand attacks the fuel. But when you have the dripping fire, you also have a lot drips landed on the fuel. So there are some similarity between it. So that makes the dripping very complicated. And clearly we need some kind of statistical analysis to help understand this problem, not just by equations. This is too complicated for simple equations to explain it. And maybe some research in the Firebrand showers can give some more ideas about the ignition, dripping ignition process. And so let me just summarize today's talk. So this is something we play in the lab. If you put the drip into the water, it can generate a tiny explosion. So this is basically the boiler over. So when we think about the drips, we should always think it's oil. It's just a burning oil particle. So these hot oil, when they attack the water, they actually can generate a boiler over. So it's very dangerous. So it makes us also question whether we can use water to suppress these drips. Okay, I think there's a lot unknowns in this area. Although we're trying to form some equations to explain these phenomena, but clearly it's just too complicated. We need some maybe statistical approach to explain this massive dripping, and maybe we have to try ignite different fuels, or maybe give some more better equations to solve these problems. But most challenging part is, I think, is the simulation. How can we simulate such a difficult process? If you just think about it, it's that there are 3 phases involved. You have solid fuel. So the solid fuel melts into liquid. Then the liquid vaporizes into gas. And there are 2 kinds of combustion reactions. First, you have the flame. And second, you have a pyrolysis in the fuel. So these are very complicated. And sometimes the plastic may not be very completely melted. So all of these increase a variable to this problem. And in the end, how can we solve this problem? How can we reduce the fire risk of the dripping? Maybe we can produce some special plastic. It can never generate drips. Or maybe when it generates drips, it can never carry the flame. Then it will be safe as well. So how can we change the chemistry in these plastic to make it a fire safe, free of dripping fire hazard? So that's basically my talk today. Okay, I hope it's not too long. Okay.
Thank you, Xinyan. It was great.
Yeah, really enjoyed that, Xinyan. Thank you. We've had quite a lot of questions from people, which is great. If anyone does want me to prioritize these questions, like the ones you like, but I'll just go through some of the ones that were asked. There was a couple about where dripping fires occur, on what type of material. One person was asking, can they occur on fabric and cellulose? Someone else asked, can they occur in chemical fires? So basically, are there other materials other than like plastics that can sustain these kind of dripping fires?
Yes, so basically there are 2 kinds of the plastic material. The first is thermoset. The other is thermoplastic. The other is thermoset. So for the thermoplastic, they are easily to melt. For example, the polyethylene. So most of the plastic, if it's very soft, it can melt. If some plastic are very hard, in general, if you heat it, it may not melt. Like some custom-made PMMA, these are not able to melt. So if the plastic is not able to melt, then it will never generate drips. So that's yeah.
Sorry, Yeah, that makes sense to me. That's kind of what I was thinking, is if your plastic's going to char or whatever, it won't make it, it's not going to drip. But I was wondering about with someone else was asking about chemical fires and sort of like where you've already got a liquid fuel. Is it a similar phenomenon if you have that liquid fuel falling, or does it burn much faster? Or yeah, I don't know. Is it?
Okay. Yeah, that's a very good question. So if it's let's say it's a gasoline, it definitely burns very fast. So maybe it will just burn out before it reach the ground. And these plastics, they are not burning as fast as gasoline. That's the reason it can last longer in the sky.
Mm. Yeah.
And also the gasoline particle is much smaller because the surface tension is small. So when you generate the particle, it's smaller, much smaller.
Yeah. Okay. And you were showing sort of the criticality of the size there as well. In fact, interestingly, there's actually a question here from Francesco. He was just asking if there was, when you're talking about the von Karman vortices and the vortex shedding, he was asking if there was a particular critical frequency or size at which point you see the vortex with or without the flame. Particularly.
Okay. Yes, that's also a very good question. Yes, you have to. So there are many problems here. So first, because the air has friction, it has resistance. So eventually the drip will reach a terminal velocity. So for these small drips, the terminal velocity is smaller. So for these small drips, it cannot even reach the critical velocity for generating vortex. But for the larger drip, it can move very fast because the terminal velocity is faster. Then that's also another reason it can generate a vortex behind it. But in general, in all the experiments we have seen, it's relatively, for most of the drips, you can generate the vortex behind it. But how stable it is, that's a different story.
Interesting. Francesco asked this actually, and I think it's a good question because you're talking about varying the mass and the frequency and stuff. But how actually did you achieve that feasibly? How were you able to control the size or the frequency of the drips?
Okay, so we trying to, so the frequency we control is we put a different metal into the plastic tube. So the metal of copper, steel, or maybe just a metal tube. So we use that, we use a conduction, heat conduction to control the drips. So if it's a copper metal, so it will cool the plastic quickly, so the frequency will reduced, and so that's we control it. But luckily, the frequency is relatively stable in most of the cases. But we have 10% uncertainty. That's fortunate.
Yeah. So that controls how fast they're coming off. But what about like the size of how big they are? Is that also?
Yes, it's also controlled by the cooling.
Okay, interesting. So are they like related? Is the mass and frequency linked then? Because they seemed independent in your thing, but you're saying like they're kind of like increasing one decreases the other, or?
So if we're trying to cool the plastic from the back, so you actually need a larger drip to overcome that surface tension because you're trying to get it done. So that's the reason the drip is relatively larger if you're trying to cool it on the back.
Yeah, and if it's larger, it's also slower frequency of dripping, right?
That's true, yes.
Yeah, okay, cool. Yeah, that's interesting. That makes sense. Yeah, here we go. Someone asking here, how can you confirm that the main reason for ignition is the flame rather than the high temperature? So yeah, you're saying when the distance of the tissue is increasing, the temperature of the drip is also decreasing by the time it hits the tissue. Yeah, I don't know if you have something on that. I guess that was related to when you talk about the different heat fluxes as well. of the two?
Okay, so we tried that with tissue paper first. So we see like 30 drips without a flame can still not ignite the tissue paper. So when I say ignition, it's a flaming ignition, not smoldering, because the paper may get smoldered. But if you have just one drip with a flame, you can ignite that tissue paper. So I think that's a confirmation. The flame is really necessary here, not the amount of the plastic drip.
Do you know why that is, or do you have a particular theory for why the flame is particularly important there?
Well, because it's a pilot source. That's what I have to say.
Yeah, that makes it. Yeah, I see. It's sort of the.
And the dripping, the cooling of the large drip is actually not that big. I recently see some other people doing experiments. They use the infrared camera to see the drips, and they see the temperature does not change that much. We can also do some hand calculation to check how much heat is lost. But in general, for like 2 mm and 3 mm drips, the cooling in the air is small because it's just too fast. It's like within 1 second, it already reached the ground.
Yeah. Yeah, I think you kind of answered this before with how you controlled it in the experiment. But Dwee was asking what affect the frequency of the drip, what parameters affected the frequency of the drip. So you already mentioned the sort of temperature of the plastic and whether it's being cooled and this sort of thing. Is there anything else that affected the dripping frequency, or was it just that?
Okay, so yes, so that's from the generation point of view. But in our experiment, we trying to test this different frequency. So what we do is, so for every other drip, we just swipe it away. So we just only allow 1 out of 2 to land on the field. That's how we vary the frequency. So we just manually control it, reduce the frequency.
Yeah, okay, that makes sense. But you don't know, but like the type of plastic or like the thickness of the wire or stuff, will that affect it in real life, not in your experiments, but like sort of?
Of course, the material itself affect because the surface tension of each plastic are different. And we haven't tried that, but there are many researchers, they do UL94 test that will generate drips for the plastic. I see some drips are very big. For some extruded PMMA, the drip is really big. Okay. But for the polyethylene PC, PP, usually the drips are relatively small.
Interesting. That's cool. There's another this is quite a technical question, so it'll probably go over my head. But someone was asking if you could comment more on your fluid mechanics simulations, on your DNS calculation. And have you dealt with the gasification process and the dynamics of the liquid gas interface? Okay. So yeah, I might not be able to understand this answer, but someone's very interested.
Okay, this is a very good question. So maybe I'll try to go back to the slide. It's we don't simulate that. Let me just put that way. So we trying to simplify the problem. We only focusing on the critical condition for the flame shielding. So we didn't simulate the pyrolysis. We only manually set the pyrolysis gas, the amount of the pyrolysis gas. So, yeah, I think this is what he's talking about.
Yeah.
Okay, so we don't. Basically what I say is. So we just set its a boundary condition. How many gas is released out from the fuel, rather than using pyrolysis reactions to simulate it. It's otherwise it's just too complicated. Okay, I don't think I can do that.
Yeah. So you're sort of saying, based on how big the droplet is, it'll be releasing a different amount of fuel, and then that's your boundary condition for the
Yes.
fluid. So yeah,
We don't use the Arrhenius equation to solve the pyrolysis.
makes sense. Yeah, that would be, I think, a whole other research breakthrough if you'd managed to do that accurately as well. Okay, that's all the questions people are asking, and that's interesting. I do have one more though, because at the beginning, from my area of research, I found interesting because you mentioned facade fires at the beginning. A lot of the dripping you were focusing on, well, I mean, you were focusing on the sort of fundamental phenomena, where it was sort of dripping down onto a surface. I was wondering if you'd looked into a tool sort of dripping along a wall, like where it's sort of it doesn't detach from the wall, so it's sort of like traveling along it, and whether you've looked into that or are planning to look into it.
Okay, so in fact, many researchers are looking on that problem. So that's flooring, sometimes they call, if it's landed on the floor, and they are generating melting flow rather than
drips.
Yes.
Yeah.
So I think many researchers from USTC, they actually look at that before.
Cool. Well, I'll get the details later. But yeah, that's really good to know. Is there anything? Sorry, yeah. Carry on.
Okay. Okay, my PowerPoint is stuck, so otherwise I can show you a slide.
Yeah. No, I was curious. Just before we go to the Xinyan Huang, I wondered if there was anything. What are the sort of next steps for this research? If you have anything coming along in the future that you'd like to tease for us.
Okay, so everything we look at is thin film. We haven't tried thick film. So next we want to try to ignite a PMMA plate, or maybe a PE plate, or maybe a wood plate. I think that's more challenging because you need a lot of drips.
Yeah.
And maybe larger drips. We're trying to figure out a way to generate large drips. It's very difficult.
Cool. Well, that sounds great, and yeah, really fascinating research, Xinyan. Thank you for sharing it. Thank you everyone for coming and for your great questions. And if you'd like to see more talks like this, as always, follow us on Twitter. Sign up to our mailing list, all of that sort of thing. We've got another talk. Francesca, what was the date of our next talk?
We have another talk next week on Monday, so the 22nd, by Dr. Isa Vermesi, a fire engineer here in London. And we have another talk scheduled for end of April. All the details are on our website, but we don't have the events are not live yet, but if you check in a couple of days, they should be on our website.
Great. So thank you again, Xinyan. Thanks everyone for coming, and have a fantastic week, everyone. See you soon. Bye.
Thank you. Thank you, Xinyan. Thank you, Matt.
Thank you.